the spatial resolution of EEG and MEG source estimation is, of course, quite fundamental for the interpretation of EEG and MEG results and everything that's done with them, like connectivity, for example, also decoding. But of course, there's very little agreement in the literature among researchers on how to approach this and how to quantify this and how to really fairly compare source estimation methods. So here's my version. And in this session, I will introduce the basic concepts, that I would use to evaluate spatial resolution. And those are mostly the resolution matrix, which sounds a bit scary because it has the word matrix in there. But there are some more intuitive concepts, the point spread and the crosstalk functions. And I think if you meditate a little bit over that, and if you get the idea of those, and if you maybe even manage to use those in your own research to look at your own methods, your own sensor configurations, and their point spread and crosstalk functions, then I think this can take you a long way to understanding what you are doing with or to your data. Okay, let's just go back to one slide that I've, I think, shown a number of times. So this is the problem we are trying to solve. We have usually more sources in the brain than we have sensors around the head. That leads to an underdetermined problem. So the data are lead field matrix times the unknown dipole strengths. We usually just have the data. We want to know the unknown dipole strengths. So we would like to turn our lead field matrix into some sort of inverse matrix, inverse operator that we apply to our data and get the dipole strengths. This would be the linear approach. There are nonlinear methods that you cannot illustrate like that, but maybe we'll do that in a separate session. And again, non-unique, linear equation at the end with fewer data points. Then we have unknowns. That's why it's underdetermined. So what does that mean for the spatial resolution of our source estimation results? And I would like to actually approach this with what I call a blurry image analogy. Imagine you're looking through a street scene, through a windscreen onto a street, and you're trying to figure out what's going on. And unfortunately, this screen is somehow blurred, in this case with raindrops. Then that means you can see some details, but not others. And you use probably some experience, some prior knowledge to figure out what's going on. But even so, certain details like the number plate here, or who exactly is walking along the street, will still be obscured to you. And I find this is the analogy, how we are trying to look into the brain with EEG and MEG. So unfortunately, there is this blurry windscreen between us and the brain, and we just have to figure out what are the properties of this windscreen. So what can and what can't we tell based on the data that we've got. For example, there might be some really strong sources somewhere, and we have some idea of what they are, street lights, but they are blurring everything around. So if there are any smaller details around, they might just actually be little raindrops in our windscreen and nothing that's actually out there. So these might be artifacts. And just like before, some areas are maybe, as I said before, some details might be completely obscured because they're in some dark place. Others might be a bit more better illuminated. Anyway, I think you're getting the idea. So we want to find out what is this blurry screen between us and the brain. Yes, and quite a few methods out there suggest that they found some mathematical trick, that manages to get you higher spatial resolution or manages to reconstruct sources better than other methods. And very often, I also get lost in the mathematics, and at some point there is a bit of magic going on. But I actually think with this approach, I think you can actually understand source estimation from a more intuitive point of view. But it is actually something that really leads to some practical, clear measures for spatial resolution that do not depend on the complex mathematics behind individual methods. And ultimately, just because the brain is complicated doesn't mean that we also always have to understand, every single parameter in our methods in order to come to our conclusions. So some things in source estimation, I think, can actually be explained quite intuitively, but I'm not sure if I'm going to succeed with this today. So one thing that is important, at least when you are using linear methods to approach the inverse problem, is the superposition principle. And that's actually something that hasn't been invented for EEG and MEG analysis. It's actually used whenever people use linear methods to look at their data. So for example, if you look through a microscope, so you can think about the microscope performing a linear operation on the image. So there's an input image. The lens of the microscope has a certain blurring function. So this is the kind of, this would be the kind of blurring that you impose with your lens, because it might not be a perfect lens, or simply because of some optical properties of the glass. So this would be like a point spread function. So if there was a tiny source somewhere in the microscope, this is the kind of blurring you would get. And this blurring would be applied to all the pixels here. But in the image, I mean, there's a process called convolution. So you move this kernel around and you basically blur the whole image. And what you then get as a result is the original, the true sources underneath your microscope blurred by this kernel, by this point spread function. And if you know this kind of blurring that you've got here, then you also know that you cannot interpret certain features. So you will never get the exact boundaries of this object back. If you have two tiny dots like this next to each other, they might get blurred into each other. So this will tell you basically what kind of detail you can interpret in your image. Another example from astronomy, I think this is the picture I found on Wikipedia from the Hubble telescope. You know, they initially messed that up. They didn't get the mirrors right. So they only looked at some blurry image of the sky. And so in this case, this is a point spread function they actually didn't want. And then somebody went up there and repaired the whole thing, and then they could look at the stars again properly. So it is something, and this is the point I'm trying to make, which is a very fundamental tool actually for linear data analysis methods to describe them. Filtering is another, frequency filtering is another example. I think we looked at impulse responses, which are basically point spread functions in the context of filtering. And it even has a Wikipedia page, so that must be useful. And also to highlight the idea again, so now we're getting a little bit closer to what we are trying to do. So they actually provide us with some methods to actually look at our specific measurement configuration and see what's going on there. So imagine you have a source estimation method, and this method will always give you, and if there's a dipole in this location, this kind of source estimate. And you know that for another dipole in another location, you get this type of blurry source estimate. Then for linear methods, the superposition principle holds. That means if these two sources were active simultaneously, you would simply get the sum of these two point spread functions. So you would get that. For nonlinear methods, that's not necessarily the case. So you might get some much more complicated interaction there. But for linear methods, that's the idea. If you have two sources active individually, you just sum up the corresponding point spread functions. So if you have another case, two sources that are closer together, these two point spread functions then blur into each other. So if you know this kind of point spread function, and if you know that it's the same for all these different locations, then you can already get an idea of the spatial scale at which you can interpret your data. So it will tell you which sources you can separate and which sources you can't separate from each other. So, and this is something we should be aiming for EEG and MEG source estimation as well. So once we know that, at least I think we are one step further, and we know at least that there's, you know, what we can hope for when we are looking at our source estimation results. Yeah, so this also would allow you to draw conclusions for more complex sources. So if you know these point spread functions for all your sources in your source space, then you can potentially test, you know, what happens if I have more complex source distributions, because all you have to do is sum up these different point spread functions. More about that later. Before we use that for something that's actually meaningful to us, just a few remarks. You know, that spatial resolution is, of course, more complex for EEG and MEG. So unfortunately, these point spread functions are not always as homogeneous and Gaussian as I just showed you. And on top of that, spatial resolution will depend on how many sensors you use and whether you use EEG, MEG, or both, and what kind of MEG system, for example. Source location will be important. So we know that sources deeper in the brain produce much smaller amplitudes than those close to the sensors. So there will be some that will be reflected in spatial resolution. We know that source orientation plays a role. Radial sources in MEG produce very small or hardly any measurable signals. They will not be reflected that well in our source estimates for MEG at least. I mean, obviously the signal to noise ratio, the noisier your data, the lower the spatial resolution, probably. Head modeling is important. I mean, this is not necessarily actually spatial resolution, more localization accuracy, still mentioning it here. So the more accurate your head model, the more accurate your source estimation will be. And also assumptions about the sources. I mean, if you have valuable, useful, a priori information about where your sources are, how focal they are, that could potentially improve, of course, your spatial resolution. So it's difficult to make a general statement. It always depends. But that's, I think, why it's important to step back a little and understand some of the basic concepts, how to measure, how to evaluate spatial resolution, which will ultimately also lead to some tools that you can use with your specific experimental setup and measurement configuration to potentially evaluate spatial resolution in your own analysis pipeline. Another bit of theory in between, so it will become a bit more intuitive after that. So the resolution matrix, I think, is the absolute central concept if you're approaching linear inverse problems. So we've seen the forward problem already, this D equals lead fields times sources. So this time I call the sources S, just to confuse everybody a little bit more. We want to approach the inverse problem with linear methods in this case. So what we are hoping for is to get an estimate of the sources, so the hat stands for the estimate, with some sort of inverse matrix G, for generalized inverse in this case, that we multiply to our data in order to get our estimate. And if we approach our inverse problem like this, and at this point we haven't even said anything about what this G could be like, it could be anything. It could fall from heaven, or it could be the minimum norm estimator or whatever. So, but as soon as we make the assumption that this is what we are dealing with, the linear forward problem and the linear inverse problem, then we can substitute this D by what we've got for D on the left side here, lead field times sources, and we get this relationship. So the estimated sources are the inverse operator times the lead field times the true source distribution. And this G times L, we can then define as R as a resolution matrix. And that is the relationship between the true sources that we would love to know, but we will probably never know in full accuracy, and our estimate. So this is what we will get in the end, and this is what we would like to know. So this is now the blurry image, or the screen, the windscreen that's between us and the brain. So this is what we are looking through. So we are seeing this. We would like to see this, but we only get a blurred version of this, and the blurring is given by the resolution matrix. And this resolution matrix is symmetric, and it's of dimension the number of dipoles times the number of dipoles, so it's quite a big matrix. But this is now what describes this type of blurring. So this is now something we can analyze, potentially visualize, or analyze, quantify. And that tells us how bad our situation really is, so how blurry our windscreen really is. We can also use it now to actually find our optimal inverse method. So this matrix G in our previous matrix, maybe we can say, well, we want the one that produces the best resolution matrix. So ideally a clean windscreen. And mathematically, we can say, what's the best? We can ask ourselves, what is the best resolution matrix? Well, the best resolution matrix would be the identity matrix, because then our estimate would be exactly our true source. So that would basically be the clean windscreen. If we write that down, we can say, well, minimize difference between the resolution matrix and the identity matrix. And if we do that with a least squares approach, then we actually get the minimum norm estimator. So I'm not going to explain that in detail. At this point, you have to believe me. But if you want optimal spatial resolution in terms of minimizing the difference between your resolution matrix and the ideal resolution matrix, which is the identity matrix, then you get the minimum norm estimator. It has the property that the rows and the columns are symmetric. That will matter in a bit. But now we can actually get a little bit more intuitive with this. So the resolution matrix is a very central concept for linear inverse problems. In practice, I think it's very useful to look at two aspects of this resolution matrix. And you can, if you want, forget what I've talked about until now. We've already talked about the point spread function. So this will tell you if there is a point source somewhere, let's say a dipole here at a particular vertex on the cortical surface. And if that's active with unit strength, how much does activity from this dipole then spread to other regions after source estimation? So if you simulate the magnetic field or the electric potential from this dipole and then subject it to one particular source estimation method, whether it's minimum norm or beamforming or Loretta or so on and so forth, and you compute the corresponding solution and you plot that, then this is what you get. This is the point spread function. So point source spreads to other regions. That is the point spread. But you can also ask, for example, when you want to do connectivity analysis, you want to extract the time course for this region. So you don't care about the others. You want the time course for this region. And you want to know, so spatial resolution is limited. So how much do other regions then leak into the time course for this particular vertex? So I don't have millimeter by millimeter spatial resolution. So whatever I extract from here will be affected by sources around this location. And this is given by the so-called crosstalk function. So how much crosstalk do I get from sources I'm not interested in into the source that I'm interested in? And these two are not necessarily the same, even when you are using the same method. So that's why you have to look at them separately. But I told you earlier, the resolution matrix is symmetric. And that means for minimum norm, actually, these two functions usually are the same. So if you plot them for the minimum norm estimator, the classic minimum norm estimator, they would look the same. And that's because the point spread functions are the columns of the resolution matrix. The crosstalk functions are the rows of the resolution matrix. So if that matrix is symmetric, they will look the same. But for other methods, that's not necessarily the case. So you have to treat them separately. And here are some examples. This is based on simulations. So I simulated a source here in the anterior temporal lobe, where you can see the green circle. This is the magnetic field or the magnetometer topography. And you can see that the topography is cut in half, more or less. But even so, even though we only sample half of this topography, spatial resolution is at least reasonable, I would say. I would still call that good, considering we know that EEG and MEG are not perfect. So you get most of the activity, spreads around the anterior temporal lobe, or the other way around, because this is minimum norm. So if you interpret this as a crosstalk function, that means if you want to extract a signal for this green circle there at this vertex, you will also get some of the activity from the whole anterior temporal lobe for free. And there are some speckles here also in other areas. And make no mistake, they are actually quite close here to the anterior temporal lobe because this is an inflated brain. Still, I would say there is a bit of leakage, a bit of blurring going on here, but what comes from the anterior temporal lobe seems to stay mostly in the anterior temporal lobe at least. If you're interested in occipital cortex, then I think you're usually quite happy. You will be quite happy with MEG. It's well covered. So this source is completely sampled very nicely here. You are close to the senses. So that means here these two peaks are actually quite close to each other. It's quite a nice topography. So, and you can see here the point spread function. It's the green circle almost covers it. So it's quite focal. It's probably not, still a bit blurred compared to the true source, which we don't know, but it will be a few square millimeters, I guess. There are some speckles around here, but it's confined to at least the left hemisphere and quite focal around the green dot, the green circle. This is something that could be in motor cortex. In this case, Also, you are sampling the topography pretty well, but here the peaks are maybe a bit further apart than for the occipital lobe, so that's why it's a bit more widespread here. But still, I would call that a good point spread functions, at least centered around the green circle. And finally, maybe a bit further up, that could be leg motor cortex or something like that, closer to the vertex. It looks similar, I would say. So these are good examples of point spread and crosstalk functions. This is what I think we can achieve with EEG and MEG. And keep in mind, this is based on simulations. So in real life, of course, you might have noisier data and you might make some additional errors. So this is probably best case scenario. There are some cases that are maybe less good. So as soon as you go into depth, you will see that at least the minimal norm estimator moves your activity closer to the sensors. So in this case, you have the peak closer to the sensors, but also quite a few side lobes here around the inferior temporal lobe. Here in orbitofrontal cortex, I mean, you get quite a bit of frontal cortex activated, even here in more dorsal regions, anterior temporal lobe. And you should also keep in mind that these sensors are, of course, further away from the frontal lobe than they are, for example, here in the back from the occipital lobe. So sensor positioning, of course, matters. And here, if we go deep into the Sylvian fissure, several centimeters under the surface, in this visualization on this scale here, you don't even see anything down there. So all of this activity spreads to the anterior temporal lobe and inferior frontal cortex, or other way around. In the crosstalk interpretation, if you wanted to extract the time course for this vertex here, you would actually get a lot of activity from the anterior temporal lobe and inferior frontal lobe. So this would completely overshadow the small signals that you may get actually from the depth of the Sylvian fissure. Could be the insula here, for example. So this just gives you an idea of what you can do with these point spread and crosstalk functions, how they can help you to visualize spatial resolution. So you could compute these, for example, in MNE-Python for your own sensor configuration. Doesn't matter whether you have 32 EEG channels or 306 MEG channels or combination of them. So this really helps you to visualize the spatial resolution of your own measurement configuration, also for different methods. So I've used minimum norm estimation to illustrate these concepts. Of course, you can play around with different methods, and that's exactly what we are going to do in one of the next sessions. You can also use these functions to quantify spatial resolution and find metrics that quantify, for example, the dipole localization or the spatial extent of these functions, so that you can do a more quantitative analysis of spatial resolution and quantitative comparison between different source estimation methods. So this is something for one of the next sessions. But at this point, I would still like to highlight that all this has consequences already for the definition of regions of interest. So don't think that if you're looking at an fMRI study and you're doing a similar study with EEG and MEG, that you can simply use the ROIs from these fMRI studies for your MEG study, because you have systematic mislocalization. We've seen that you may have systematic mislocalization of deeper sources to more superficial sources, for example, or from the Sylvian fissure into inferior frontal and superior temporal regions. So this is something you would need to take into account when you define regions of interest in MEG studies. And there are ways of potentially optimize regions of interests and parcellations for EEG and MEG source estimation. I mean, this is one example from our group here, Farahi Buzorg et al. So where we basically use the idea of crosstalk functions to make sure that we end up with parcellations that have minimal crosstalk between parcels, but maximum crosstalk for vertices within parcels. So if you're interested in that, have a look. Otherwise, we will look at this in a bit more detail in another session, or at least another session.